Hey everyone, ever stop to wonder what holds, well, everything together? We're talking about the literal glue of our world. It's this incredible, invisible partnership between atoms that makes everything from the water we drink to the air we breathe possible. So, what is this force?
Seriously, just think about that. You are made of atoms. The chair you're sitting on, the phone in your hand, it's all atoms. What stops all of it from just poof, drifting apart? What's the organizing principle that turns a chaotic soup of atoms into the stable stuff of life?
Well, the secret lies in what you could call an atomic handshake. Take water, for instance. You've got two hydrogen atoms and one oxygen atom. They don't just randomly hang out together. No, they link up to form a brand new, super stable unit, a water molecule. And this all happens through a process called bonding, and we're about to dive into exactly how it works.
To really get why atoms bother to bond in the first place, we have to understand their motivation. And like so many things in nature, it all boils down to one simple drive: the search for stability. And there's a powerful rule that governs this whole process.
It's called the octet rule. Okay, picture the noble gases, that column on the far right of the periodic table. They're the super stable, unreactive, kind of cool kids of the atomic world. And why are they so chill? Because their outermost shell of electrons is completely full. For most, that magic number is 8. 8 valence electrons, to be precise. And pretty much every other atom out there is trying to get to that same stable state.
So how do they do it? How do they get to 8? Well, they've got two main game plans. The first is an ionic bond. That's basically a giveaway. One atom donates an electron and another one snaps it up. But today, we're focusing on the second strategy, the covalent bond. And this one isn't about giving and taking. It's all about sharing.
All right, let's dive into that sharing partnership. So a covalent bond is what happens when two nonmetal atoms share electrons so they can both hit that stable number. But what does it actually look like for atoms to share electrons?
Let's make this real with a classic example, a chlorine molecule. So a single chlorine atom has 7 of those outer valence electrons. It's so close, it just needs one more to get to that stable octet of 8. Now, what happens when it bumps into another chlorine atom who's in the exact same boat? Well, neither one is strong enough to just rip an electron off the other. So they do something brilliant. They compromise. Each atom puts one electron into the middle, and they form a shared pair that sits right between.
And here's the absolutely clever part. That shared pair of electrons, it counts for both of them. So the chlorine on the left can say, okay, I've got my original 6, plus these two we're sharing, that's 8. And the one on the right does the exact same math. Boom. They're both stable, they've created a single covalent bond. It's the perfect atomic win-win.
Okay, so that seems pretty straightforward, right? But is the sharing always equal? Is it always a perfect 50-50 split like we just saw with chlorine? Oh, definitely not. And this is where the story gets really interesting.
Yeah, the answer is a big no. You can imagine a covalent bond as a tug of war for that shared pair of electrons. With our two chlorine atoms, they were identical twins, pulling with the exact same strength. It was a perfect tie. But what happens when you have two different atoms pulling on that rope?
This is where a super important concept called electronegativity comes into play. It's really just a word for how much pull an atom has on shared electrons. Just look at this periodic table. You can see elements like fluorine and oxygen. Up there in the top right, they have really high electronegativity. They're like the champion weightlifters in this tug of war. Meanwhile, the elements down in the bottom left, not so much pull. So check this out. On the left, two hydrogen atoms. Same atom, same pull. They share those electrons perfectly equally. The electron cloud is symmetrical. We call this a nonpolar covalent bond. But now look at the right, hydrogen chloride. Chlorine is way more electronegative than hydrogen. It yanks that shared electron pair closer to its side. This makes the chlorine end a little bit negative and the hydrogen end a little bit positive. And that is a polar covalent bond.
What's really cool is that we can actually predict the bond type just by doing some simple math. All you have to do is find the difference in the electronegativity values between two atoms. If the difference is tiny, between 0 and 0.4, the sharing is equal. It's nonpolar. If it's in that middle range, about 0.5 to 1.8, the sharing is unequal. It's polar. And if the difference is huge, over 1.8, well, one atom pulls so hard it just takes the electron completely, and that's an ionic bond.
Okay, so we've got the bonds down, these lines that connect atoms. But molecules aren't flat drawings on a page. They're 3D objects.
So how do these bonds arrange themselves in space to create the actual shapes that give everything its unique properties?
Well, our first step is to create a kind of 2D blueprint. This is called a Lewis structure. It's a simple diagram that just shows us which atoms are connected to which, and it maps out where all the valence electrons are, both the shared ones in bonds and the unshared ones, which we call lone pairs.
Now, to go from that 2D blueprint to a 3D shape, we need one more crucial idea. And it's really simple. Electrons are all negatively charged, so they repel each other. VSEPR theory, that's a mouthful. It stands for valence shell electron pair repulsion, is built on this idea. It just says that all the groups of electrons around a central atom will push on each other until they're as far apart as they can possibly get. They all want their personal space.
Let's circle back to our water molecule to see this in action. The central oxygen atom is bonded to 2 hydrogens, but it also has 2 of those lone pairs. That's 4 groups of electrons all pushing each other away. And it turns out the lone pairs are a little extra pushy. They shove the hydrogen atoms down and closer together, creating that famous bent shape of a water molecule. And that shape is everything. It's what makes water polar, it's why it can dissolve so many substances, and it's the foundation for properties crucial for life itself.
So we've gone on quite a journey here, right? From a simple rule about atoms wanting to be stable, all the way to the complex 3D shapes of molecules. Let's zoom out one last time and connect these tiny, microscopic rules to the big world we see all around us.
So here's the whole story in a nutshell. Atoms share electrons in covalent bonds to get stable. That's the octet rule. How they share depends on electronegativity, which tells us if a bond is polar or nonpolar. And finally, all those electron pairs push each other apart to create the molecule's final 3D shape. And that's it. Those few simple rules are the blueprints for pretty much everything.
When you really stop and think about it, it's pretty amazing. This simple idea of an atomic handshake is the foundation for the unbelievable complexity we see in the world, including life itself. It really makes you wonder, doesn't it? What other elegant, simple rules are out there, hiding in plain sight, just waiting for us to discover them?